So for the next proof technique, we're going to reason by contradiction. And here the idea is that we have an implication P implies Q that we want to prove. And so what we're going to do here is we're going to assume that Q is not true. And we'll still assume P, that's the thing that we're given, and then we'll try to obtain a contradiction. This is also often a useful technique when you can't proceed with the direct proof. What you do is you assume that the thing that you want to prove is not true, and then you try to find a contradiction. And once you have that contradiction, you go back to your assumption that you made that Q is not true, and that led to a contradiction. So therefore, the negation of that must be true. So Q itself has to be true. So let's look at an example. So let's prove that if x times x minus 2 is equal to 0 and x is different from 0, then x is equal to 2. So you could do this with a direct proof, but let's do it with contradiction. So we start by saying assume that the thing that we want to prove is not true. So assume that x is different from 2. So then what we have from that is that x minus 2 is different from 0. And now if we go look at what we're given, x times x minus 2 is 0. And we've just established that this factor is not equal to 0, so we can divide it out. And from that we get then that x is equal to 0, because the product of two things is 0, and one of those two things is not 0, the other thing has to be 0. And now we've arrived at a contradiction, because in the givens we also have explicitly given that x is different from 0. And now the fact that we've obtained a contradiction here means that our initial assumption, which I'm indicating in brown here, that assumption was false. And we assume that x is different from 0. If that assumption is false, that means that x is equal to 2. And that was the thing that we have to prove. So by contradiction, we arrive at the thing that we wanted to prove. So now continuing, let's talk about equivalences. So equivalences are basically relations where you have two logical statements that are equivalent, or where equivalent meaning that one is true if and only if the other one is true. So if we have two logical statements P and Q, we denote equivalence by this arrow that has double arrow with angles on both sides. So P equivalent with Q. P is equivalent with Q, or in other words, and maybe a bit more verbose, P is true if and only if Q is true. And this if and only if, that's a standard mathematical formulation for equivalence, so keep that in mind. And in textbooks you often see this abbreviated as if with two F's. So if and only if So let's look at an example of an equivalence. Let's prove that n is even if and only if n squared is even. So if we write it a bit more formally, n even equivalent with n squared even. So how do you prove this kind of equivalence? Well, the notation already indicates it a little bit. So this statement is the same as saying that P implies Q and Q implies P. So these two things have to hold at the same time. So our proof is also going to fall apart into two separate parts. So P implies Q and then Q implies P. So here our P is n even, our Q is n squared even. And so now we can proceed. So let's start with n being even. That means that we can write n as 2 times k for some k, a natural number. And then n squared is 4 times k squared. And in particular, that's 2 times 2k squared. So you see that this is, again, an even number. So 2 times anything always gives you an even number, remember. So here we conclude that n squared is also even. So that gives us 1/2 of the implication. And then the other half of the implication is, of the equivalent is Q implies P. And for that we have to prove, in other words, that n squared even implies n even, and that we did a little bit earlier, so C before. And then the last big class of statements is what do you do if you have a single statement. So we've already seen logical forms that say P implies Q. We've seen P is equivalent with Q. And now how do you go about proving a single statement P? So someone says there are infinitely many primes, or the square root of 2 is irrational. Proving a single statement. So here let's do an example. So here we're going to recap a very famous proof. Prove that the square root of 2 is irrational. And irrational means that square root of 2 is a real number, but not a fraction. So it's in the set of real numbers minus the set of fractions. So in other words, square root of 2 cannot be written as a fraction P over Q. And so many of the proof techniques that you've already seen can be applied here as well, because basically what you have is, and I should maybe state it as a general property, so a single statement is basically also an implication. But it is an implication where you start from a statement that is trivially true, and then you prove the thing that you want to prove. So in a nutshell, things like proof by contradiction are also going to work here, and they'll even be a bit simpler. So let's go back to our square root of 2 and let's prove that. So let's proceed by contradiction. And contradiction is a very good technique to use here. because we want to say something about, well, it cannot be written in a certain form, and cannot is always a bit difficult, because if you want to prove that something is not of a certain form, well, how do you do that? So contradiction here is very powerful, because let's assume that square root of 2 can be written as a fraction p over q, and now let's reason our way towards a contradiction. So here in particular what we're going to do is we're going to also demand that these p and q, so p and q are natural numbers. That's the definition of a fraction, but without common factors. So for instance, if I write 2 divided by 10, that is a fraction, but the numerator and the denominator have a common fraction 2, and I can simplify this as 1 over 5. So 1 over 5 is a fraction that has no common factors. So now, given that I can always simplify a fraction to have no common factors, I can just divide them out. I can demand the same thing for p over q, that they have no common factors. And now let's use that and reason. So let's take the square. Then we get 2 is equal to p squared over q squared, and we can write this as 2 times q squared is equal to p squared. So now this tells us that p squared is even, because we've just written it as 2 times something else, some other natural number. That implies that p squared is even. And now p squared being even, that implies that p is even, and that is because we have already proven that on one of the previous slides. And now p being even means that we can write p as 2 times k for some k. And now if we go back to the statement that we had earlier on, or rather this form, then we can substitute p is 2k in there, and we get 2 times q squared is equal to 4 times k squared, and in other words q squared is equal to 2 times k squared. And now this means in turn that q squared is even. And now if I continue below here, that tells me that q itself is even, also by the same reasoning. And finally that means I can write q as 2 times L. And now let me lift out the 2 conclusions that I've obtained. Well, I've written p as 2 times k and q as 2 times L. So p is 2k and q is 2L. And that gives me my contradiction, because here I assumed that I could write square root of 2 as p over q, with p and q not having any common factors. And here I have shown that they do have a common factor, the 2. So therefore I've ended at a contradiction. We have the lightning symbol here, and therefore my starting point, my assumption here has to be false. And I can conclude that the negation of this statement holds, so I can say square root of 2 cannot be written as a fraction p over q. So one last proof technique before we move on with mathematical induction is this so-called case enumeration. And this is also a good technique, because sometimes you can divide your proof into several subcases, which are all individually easier. So let's do this by an example. So let's try to prove that for all x and y real numbers, we have that absolute value of x times y is absolute value x times absolute value of y. And so here the idea that we're going to use is we're going to split into subcases and prove each case separately. And the caveat is don't forget any cases. So for example, there's a few natural cases that we can look at. We know the absolute value function has different behavior depending on whether the argument is positive or negative. So let's divide it up into 4 cases for each of the different signs of x and y. So the first case, let's take x greater than or equal to 0 and y same. And in that case, we have that the left-hand side is absolute value of xy. So here, if both are positive, then x times y is also non-negative. So then the absolute value of xy is just xy. And that is absolute value of x times absolute value of y. Because for positive x, the absolute value is just the number itself. So that gives us the thing to prove when both arguments are non-negative. And now let's assume that y is less than 0. So in this case, x times y, a positive times a negative number, that gives you a negative number, or 0 if x is 0. And so in this case, x times y, absolute value, is minus xy. And we can write it as x times minus y, and then that becomes absolute value of x times absolute value of y. So here we use the fact that absolute value of y is minus y for y negative. So that proves our theorem in that particular case as well. And then there's the opposite, so x negative and y positive or 0. So this is very similar, and I'll let you check this. And then the last case is both x and y negative. So now product of two negative numbers is a positive number. Then absolute value of x times y is just x times y, and we can write it as minus x minus y is absolute value of x times absolute value of y. And so in doing so, we've exhausted all of our cases and we've proven the statement for all x and y.